Hello friends. Now in today's lecture we discuss the most important point or the topics of the metrology, that is limits, fits and the tolerances. So let's begin. Now we know that many times when we see two items, two parts or the components, they look similar to each other, but if we measure the dimension of these two parts, the dimensions are not same. Now why this happened? The dimensions, they may vary in micron or in nanometer or sometimes in mm also. So we know that in nature the two things we cannot manufacture by any manufacturing process which are identical in measurement, because there are a lot of factors which contributes to the measurements. So due to that factors we have to consider some tolerances. Now the tolerance means what? A tolerance means it is some permissible limit for the variation in the dimension. The fits, it depends upon the given tolerances. So here in the introduction part it is mentioned no two parts can be produced with identical in the measurements by any manufacturing process. To produce any part, that parts is designed or governed by 5 M. Now these 5 M's, the first M is the man or the main, the second M is the material, the third M is the machine, then the 4M is the money, and the fifth one is the management. So out of this 5M, this 3M is responsible for the dimension, that is man, material and the machine. Whereas this money and management, they are needed for the smooth running or the production of any component or the parts. Now if there is any variation in man, the operator, or the material, that is raw material, and the machine, then there are some differences in the measurement. Now in any production process, regardless of how well it is designed or how carefully it is maintained, a certain amount of variation, which is natural, will always exist. So it is called as natural variability. Now what are the sources of this variation, natural variation? The first one is improperly adjusted machines. So there are a lot of factors in improperly adjusted machines. The first is, let's say, the wear and tear of machine parts which are in contact with each other. The second is vibration. The third one is the damping, if the damping is not proper. Then we can say the jigs and picture, if they are not proper, then the holding or the guiding of the tool is not proper, and again it will result in the variation in the dimension. So these are some factors which are related to the machine. The second is the operator error. Sometimes the operator has few years of experience, sometimes he is new one. So this operator error, it depends upon the skill of the operator. Sometimes though the skill is very highly skilled operator, but due to some random factors, let's say the operator is not feeling well, okay, so he will not concentrate on the workpiece or the process, and then it will result into variation. So this factor which contributes to the variation. The third one is tool wear. This tool wear is inevitable, we cannot avoid the tool wear. Any tool has some life, let's say 3 months, or sometimes it depends upon the number of parts produced. Again, this tool wear, it depends upon the material. If the material is very hard, or the difficult to cut, then the tool wear is rapid. If the material is soft, then the tool wear is slow. Then the fourth one is the defective raw material. If the raw material is not proper, it has some defect, then again it will lead to the variation. So what is the defect? Defect means, let's say, the point defect or some defect at atomic level, then the line defect, porosity, etc. So these defects, they contribute to the variation. So such variations, they are called as assignable causes, and this can be controlled. This can be controlled, but up to some limit. After that, we cannot control this variation, and that's why we provide some allowances, that's called the tolerances, to overcome or to compromise with this variation. So due to these variations, it is impossible to produce a part to an exact size, or we can say the basic size. For that purpose, some variation, which is known as the tolerances, need to be allowed. So this permissible level of tolerances, it depends upon the functional requirement, which cannot be compromised. The functional requirement of the component, machine component, mechanical component, or the component which is going to assemble with other mechanism. Here, no component can be produced or manufactured precisely to a given dimension. It can only be made to lie between two limits, which is called an upper limit and the lower limit. So designer, the R&D department, they have to suggest some tolerance limit to ensure the satisfactory operation. And the difference between the upper limit and lower limits is termed as permissive tolerance. So if the part or the object lies between these two limits, then it is acceptable. The green tag will be given to that part. Now we'll see different types of tolerances. Before that, we'll see one example. Let's assume there is one shaft which has to be manufactured, let's say, with the help of a turning process, which has a diameter of 40 mm, the basic size, and the tolerances given by the designer is plus minus 0.02 mm. So this shaft has a basic size of 40 mm. Now this shaft will be acceptable if its diameter lies between the limits of the sizes. Now what are the limits? The upper limit is 40 plus the 0.02. So 40.02 mm is the upper limit, whereas the lower limit is 40 minus 0.02 mm, that is 39.98 mm. So the total permissible tolerance for this example is 40.02 minus 30.98 is equal to 0.04 mm. So it is nothing but the 40 micron. That is the tolerance. So I hope you understand what is the tolerance. Now what is the need of the tolerance or limits and fixed? So now the today's era is a mass production or automation era. In this today's nowadays we have to produce the parts by mass production and by specialization. Then the standardization, one dimension is sufficient, or we can say there are some special purpose machine. They produce the parts at a larger quantity in the given time. And the third one is interchangeability. Nowadays, no one manufactures all the parts at one place. If you take any example, let's have an example of the centrifugal pump. So centrifugal pump has lot of parts, casings, bearings, bushings. Okay, so all these parts, they manufactured at different location A, location B, location C. Then they brought together to assemble at one place. Now for ease in the assembly, for simple or to reduce or to avoid the delay in the assembly, this interchangeability concept should be there. And to achieve this interchangeability, we have to provide some tolerances. Now the tolerances. To satisfy the ever increasing demand of accuracy, we need the tolerances. But our aim should be like that the parts they have to be produced with a less dimensional variation. The third one is it is essential for the manufacturer to have an in-depth knowledge of the tolerances to manufacture parts economically. It should adhere to the quality and the reliability. Without compromising these two, quality and reliability, the part should be manufactured. And the third one is to achieve an increased compatibility between the mating parts. So while providing these tolerances, all these points we have to remember. What is the tolerance? Tolerance is it is the algebraic difference between the upper and lower acceptable dimension. So suppose there is a hole of 50 plus minus, or let's say 50 plus plus 0.05, 0.01. So what is the tolerance for this? So the upper limit UL is equal to 50.05, whereas the lower limit LL is equal to 50.01. So total tolerance is equal to 50.05 minus 50.01, it is 0.04. So 40 micron. So this tolerance, it is an absolute value. Tolerance is an absolute value. What is the basic purpose? The basic purpose is to permit the dimensional variation in the manufacturing of the components. We know because of due to this 3M, that is man, materials and machine, it is impossible to produce two parts which are similar in the dimension, identical in the dimension. That's why you have to provide these tolerances. But the constraint is we cannot compromise in the functional requirement. That is the performance criteria. Now, what are the different types of tolerances? So we have four types of tolerances. The first one is unilateral, then the bilateral, the compound one, and the geometric tolerances. So this fourth one is geometric tolerances. It is the vast field. A separate topic, or we can say the separate subject, might be there in geometric tolerances, because in industry there is department GD&T, that is geometric dimensioning and tolerances. There are some certification in this GD&T. It is one of the crucial topic of the metrology, or we can say the mechanical engineering. All this we'll see one by one in the detail. So first we'll see what is the unilateral tolerance. If the tolerance says or tolerance distribution is on only one side of the basic size, then it is called as the unilateral tolerance. It may be a positive or negative. Positive or negative. So suppose here, let's say this basic size, okay, and this is shaft. So the tolerance says it will be a tolerance on this side. The first case, or the tolerance it may be on this side. So this tolerance is it is on positive side, this tolerance is on negative side. Suppose this side is basic is 50 mm, and let's say this is 0.07, 0.02. Suppose it is 0.05, 0.01. So in this case it is 50.07, that is the upper limit. Lower limit is 50.02. In this case, what is the upper limit? Upper limit is 49.99 and the lower limit is 49.95. Here we have to subtract this 0.01 from the basis size, that is from the 50. Here two diagram is shown for the unilateral tolerances. Below zero line is the negative. Now you can see here in the diagram a zero line, and it is the green color is the tolerance zone. It is the lower limit from this point to this point, whereas it is the upper limit. So the tolerance is here 50 plus 0.000. Second one is minus 0.06. So total tolerance here is 0.06. The second case, again zero line, lower limit and the upper limit. Here both the tolerances are on negative side. One is minus 0.110 and the upper is minus 0.07. So the total tolerance, it is called total tolerance. So it is, let's say, 50 minus 0.070 minus 50 minus 0.110 is equal to, so 50 minus 0.70, so it is 49.930 minus 49.890. So if you do the calculation here, we got is 49.890. So it is 0. So here 13 minus 940. Here 0. So total is 0.040. So the total tolerance, this total tolerance here is 0.040, 40 micron. Though this looks like the greater one 11070, but here the tolerance is 40. In this case, the total tolerance is 60. Now, unilateral tolerance is the case is positive one. Earlier it was the negative one. So positive ones, in this case, both the tolerances will be above x value, above zero line. So case 1 and the case 2. In case 1, you can see here, one dimension is nothing but the basic size, that is 0.000. Second one is 0.040. Again here, the total tolerance is 50.040 minus 50.000. So the total is 0.040 total tolerance. In this case, again, we have to add this 50.070 minus 50.030. Subtract this one, so you will get 0.040. So that is the total tolerance. I hope that you understood this topic. Now, before going to bilateral tolerances, we'll see a few points regarding this unilateral tolerance. Now, when we have to provide these unilateral tolerances, the first case, when we require a precision fit. When we require a precision fit, then the unilateral tolerance is applicable. Second, when two meeting parts, the hole and shaft, they are manufactured by the same operator, then only we provide the unilateral tolerances. The third one, it mostly provides in the drilling, because in drilling the deviation in the size is possible and maximum time or always the hole is oversized. In that case, we provide the unilateral tolerances. And the fourth one is basic size is used as a go gauge in case of unilateral tolerances. What go gauge? So these 4 points you have to remember. Now the second one is the bilateral tolerances. Now when this tolerance distribution is applied on the either side of the basic size, one tolerance will be on positive and one will be on negative, then that is the bilateral tolerance. You can see here case 1 and the case 2. Zero line here 50.020 and 50 minus 0.040, that is, if you see here 50.020, and if you subtract this 40 micron from the 50, it is 49.960. So the total tolerance will be 60 micron. 0.060, yes, it is 60 micron. Similarly here, if you do the calculation, tolerances will be 50.020 minus 49.960. 980. So 0.40. So 40 micron. So that is the bilateral tolerances or bilateral tolerance when it is provided on either side of the basic size. Some point of this bilateral tolerance, that is, it is not necessarily that zero line will divide the tolerance zone equally on the both sides. So you can see here in first case, on upper side there is 20 micron, whereas on lower side or negative side it is 40 micron. But in case 2 it is equally divided. So it may be equal or unequal. So it depends upon the functional requirement. Now the third one is compound tolerance. So the compound tolerance where more than one dimensions are required for defining this compound tolerance. So in this diagram, if you see that for the dimension r, we have the dimension r. Now to define the tolerance for this r, we have to consider the combined effect of this 40, this 20 and the 60 and their tolerances. Because if you take 61 here, then this distance will increase. If you take this 15, suppose 60 degree plus minus 2 degree. Suppose this 60 degree is on the lower side and it is 58 degree. Then the effect of this angle on this r will be like this. This line will act like that, and this r distance will decrease. Similarly, if the angle is on upper side and suppose it is 62, then what will happen? The angle will increase like this, and this r distance will increase. So to define this dimension r or its tolerances, we have to take consideration. We have to consider the remaining three dimensions. That is called as compound tolerance. Now we'll see the geometric tolerance. So in geometric dimensioning and tolerances, GD&T, it is the method of defining the parts which is based on how they function within the standard symbol. So mainly 3 or 4 point, that is form tolerance, positioning, orientation, and their circle. Form, position, then say orientation, and the runner, and their subtype. So straightness, roundness, cylindricity, flatness, all this comes under geometric dimensioning and the tolerance. So in this diagram, workpiece is given. This workpiece has a step diameter, x, and it has a diameter k. So feature control frame. We have to show the GD&T, geometric dimension and tolerances in this frame. So the first symbol shows the which type of tolerances is this. Second is dimension or value or magnitude. And third one is the reference. Tolerance, symbol, magnitude, and the reference. So diameters of the cylinders need to be concentric with each other. Diameters of the cylinders need to be concentric with each other. Here you can see concentric. Then second one, for proper fit between two cylinders, both the centers should be in the same line. Now this information is represented in the feature control frame. And this feature control frame comprises 3 boxes, which you have seen. Now first box, on the left side, it indicates feature to be controlled. Which feature you have to control? It is represented symbolically, example concentricity. Then the center box. So center box indicates within the center box. Center box indicates the distance between two cylinders. Centers cannot be apart by more than 0.0 mm. If the centers they are apart more than 0.01 mm, then this part will not fit in the mating part, and then it will get rejected. And the third box will indicate the data or the reference. So that is geometric tolerance. Now we'll see what is the maximum and the minimum material condition. Here, consider a shaft with a dimension of 40 plus minus 0.05 mm and a hole having a dimension of 45 plus minus 0.05 mm. So what is the maximum material limit and the least material limit for the shaft? So for the shaft 40.05, that is the maximum material limit. You have to add this 0.05 in the 40, that will be maximum material limit. For the least material limit or least metal limit, we have to subtract this 0.05 from the 40. So here we get 39.95 mm, the least material limit for this shaft. Okay. But for the hole, the maximum and least is different. The maximum material limit is 44.95. Here, if you subtract, it is 40.05 and one is 44.95. So this 44.95 is the maximum metal limit in the hole. Means we can reach from max to least, but we cannot travel reverse from least to max. Similar case in the chart also. We can travel from max to least, but we cannot travel least to max. Why? Suppose you have drilled a hole of 44.95, but that hole is not correct. So you can again give one cut and you can make it, let's say 44.98. That is possible. But assume that you have made a hole of 40.05 and you have to make a hole of 45 from that. Is it possible? No. Or it is a hole is a oversized hole. We cannot reduce the dimension. That is the diameter. And that hole or that shaft or that hole we can resize if it has a maximum metal limit. Similarly, in case of shaft, the shaft has a dimension of 40.05 mm diameter, and suppose the requirement is, let's say, 40.02. So we can give one cut. Okay, after that one cut, we can remove the 30 mm material and then we will reach to 40.02. But suppose the shaft is the diameter of 39.95 and that part it is not getting fitted in the hole, or we can say it is just sliding or rolling, and that is not the case. We have to make it 40.02. So it is not possible to do from 39.95 to 40.02. So that's why we always travel from max to least, but we cannot travel from least to max. So for shaft, it is 40.05 max, 39.95 least. So just you have to subtract the tolerance. But in case of hole, always remember what are the minimum size, that is the max. What are the maximum size here, that is the least material limit. So for shaft and hole, it is vice versa. In next lecture, we'll see the different types of fills. Thank you.